Maximal margin classifier, maximal margin classifier that use the hyperplane and the distance concept. So let's consider this very simple classification task. We have red point and blue point, and we want to find linear decision boundary like this that can discriminate the blue point and red point. Actually here, because the data points are very well separated, there are a bunch of different linear functions that can separate blue and red point, and it is hard to say which line is the best. Maximal margin classifier provides one very nice measurement that can assess the quality of the line, which is called margin. So what is the margin? Literally, the margin is the distance to the decision boundary, to the hyperplane that separates the two classes. So from each data point, you can measure the distance to the hyperplane, right? Among all distance values, what is the most important value is the least one. Which one is the closest data point to the decision boundary? The margin is the distance to the closest point. Okay, and the maximal margin classifier is we want to find the classifier or hyperplane that separate the red and blue point, not only separate the red and blue point, but also have the largest maximal margin, the distance to the closest point. Okay, so from this, we can define an optimization problem that can find the maximal margin classifier, that is, maximize the margin M by controlling the hyperplane parameter beta 0, beta 1 up to beta p when each point belongs to p-dimensional space, when the input predictor has p different features. We can control the beta 0 to beta p parameters. And with constraint, to easily measure the distance to the hyperplane, we want to constrain the norm of beta vector that consists of beta 1 to beta p equal to 1, so that fx equal to beta 0 plus inner product between beta vector and x, which basically give you the distance, and the sign of fx give you which side each data point belongs to. And this is the first constraint. We want to make sure the beta vector has unit length, and also we want to make yi times f, so fxi greater than or equal to m. Of course, this function is controlled by the beta values, so I will use this notation f beta. And why I multiply yi? So yi is either -1 or 1. So 1 if the data point I belong to red class, and -1 when the data point has blue color. Then since the sign of this function tells you which side your data point belong to, the yi times fb give you the true distance. If the sign of fi and sign of f beta are different, then which means your red point, either your red point belong to opposite side or your blue point belong to opposite side. So which is not good at all. We don't want this situation. So we want to make sure the product of yi and f beta xi always positive. And since this value yi f beta xi give you the distance to the hyperplane, we want to this distance greater than or equal to this margin m. And then we want to make the margin is maximized by controlling parameter beta 0 to beta p. Okay, so we want to make every data point has distance more than m, so this is the margin, and we want to maximize this m by controlling parameter beta 0 to beta p. So this is called maximal margin classifier.